Welcome back. Today we're going to talk about sampling distributions. We're going to develop a particular sampling distribution, which is the sampling distribution of a single sample mean. That is, we're concerned about just taking a sample with one variable, calculating the arithmetic mean. To derive a sampling distribution, we're going to rely on the central limit theorem, or the CLT. Well, what is a sampling distribution? In short, a sampling distribution is a theoretical distribution that is a picture of how chance operates on a particular statistic. And again, the statistic we're looking at today is a single sample means. As a picture of chance, the sampling distribution associated with a single sample means is really good for us because it's going to be normally distributed. So everything we know about normal distributions, the shape and the dispersion, and how to use z-scores to use the table in the back of the book comes into play here. This is really the importance of that material on z-scores. The central limits theorem has a lot of math behind it, but we're going to break this down and make it a little bit easier. Here's a summary of what the central limit theorem tells us. If you have a population and you're measuring a variable y in that population, and variable y will have a mean, mu, and a standard deviation of sigma. That is, if you actually had access to the entire population, you could calculate those two population parameters or population statistics. Now think about taking a sample from that population. Well, what if you could take more than one sample? 2 samples, 3 samples, 4 samples, 1,000 samples, 10,000 samples. In fact, there's a finite number of samples you could take, even though it might be very large. Here's what the central limit theorem tells us. If you take repeated random samples of a fixed sample size, and particularly if your sample size is large, then the distribution of all the means from all the samples, that is the distribution of sample means, will be approximately normally distributed with a mean equal to the population parameter, and it will have a standard error equal to the population standard deviation divided by the square root of n. And here when I say standard error, we're really talking about a standard deviation of a distribution of numbers that are all means of every possible sample you could take. If you generate this particular distribution, this sampling distribution, it's a picture of how chance operates on means because it represents the outcome or the mean of every possible sample you could take. What makes one sample different from another sample? Random sampling or chance. You take one sample, you get it by chance, and you'll have a mean associated with it. And you hope that that mean represents the mean of the larger population. You take another sample from that population randomly, and you'll get another mean. Hopefully it'll be close to the first mean, and hopefully it will be representative of the larger population. Sometimes it will and sometimes it won't. But if you could do this for all the possible samples, you'd have a picture of every outcome you could get by taking every possible sample. What makes them different? Chance or random sampling. At the end of this, we can say symbolically that mu sub y is equal to y bar sub y bar. That is, the mean of all the sample means is equal to the population parameter. And this is known as this is the definition of unbiased. If you have the mean of all, if the long run average of all your sample statistics is equal to the population statistic, then your sample statistic is said to be unbiased. And the standard deviation of that distribution of your statistic, in this case the mean, is equal to sigma sub y bar equals sigma sub y divided by the square root of n. Now I called this a standard deviation, and in some sense it is. It measures the dispersion of the sampling distribution. But as I said, the only reason that you get different means from different samples is due to chance, as long as you're using random sampling. So this is called a standard error to represent the variability in error due to sampling. Looking at this slide, I've made a population that has 5 cases in it. The cases are numbered 1 through 5. And respectively, they have the individual values of 42, 31, 100, 88, and 76. The mean of those values is 67.4. That is, mu sub y is 67.4. Now, on the right side of the screen, you'll notice that I've taken samples of size 2 from that population that has 5 cases in it, 5 elements in it. So, for example, I could draw case number 1 and case number 2 with respective values of 42 and 31, and if I average those together to get y bar, the average is 36.5. Now, I think that 36.5 is not a very good estimate of the 67.4. It's not very close to that. But let's look at another sample we could take. Sample number 2 consists of case number 1 and case number 3 with respective values of 42 and 100. If I average those two values, I get 71. Well, 71 is a lot closer to 67.4. That is, this estimate, this y bar as an estimate of mu sub y, is a lot closer. If you look at the column labeled average, you can see that some of those estimates, some of those y bars are very close to 67.4, and some are very far away and are poor estimates. Why do we get all these different averages? Because we're randomly sampling. I'm going to only take one sample to actually do my analysis. I'm going to get one of these samples. One of these numbers will be my estimate. So we're seeing all the possible outcomes we could get from sampling two things from this population of 5. Some provide good estimates, some provide weak estimates. But note at the bottom that the mean of all those means, if I average 36.5 and 71 and 65 and so forth, the mean of the means, y bar sub y bar, is equal to mu sub y, or the population parameter, or 67.4. In the upper left, I've drawn a distribution that shows the distribution of those averages, the 36.5, the 71, and the so forth, and I've superimposed a normal distribution over it. And you remember back from the central limits theorem, it said as our sample size increases, our sampling distribution becomes increasingly more normally distributed. Now, this is a very small sample size. It's about the smallest sample size you can take and still calculate an average, sample size of 2. And even with this very small sample size, you can see pretty quickly that the distribution of these numbers is pretty close to the normal distribution. At the bottom of the screen, you'll notice that there's a link down there. Copy that link down and go to that web page, and there's a nice demonstration, software demonstration you can run that will test your understanding and demonstrate to you the notion of the central limits theorem and repeated random sampling. So what does this mean? Well, first of all, if we happen to know population mean and population standard deviation and the number of cases of a sample, we can immediately calculate the standard error. In this example, I have a mean of 100 and a standard deviation of 15. That's mu and sigma respectively. Remember, mu and sigma imply that this is taken from that these numbers were associated with a population. With samples of size 400, my standard error is equal to 0.750. That is, it's 15 divided by the square root of n. Take a close look at that notation. It's sigma sub y bar. We know that sigma sub y is the standard deviation of a population, and sigma sub y bar is the standard deviation of the sampling distribution of y, that is the distribution of all possible sample means, and more technically we call that the standard error. I can put something called a 95% confidence interval around my average value. So you can see there that CL sub 95, the confidence limit for 95% confidence limit, is equal to mu sub y plus or minus 1.96 times 0.750. 0.750 is basically a standard deviation. We know that in a normal distribution, if we go plus or minus 1 standard deviation, we capture about 68% of all the cases. If I were to go 1.96 standard deviations, I would capture approximately 95% of all the cases. My 95% confidence limit here goes from a low of 98.53 to a high of 101.47. So what exactly lies plus or minus 1 standard error, or 0.75, around the mean? In this case, if we were to take repeated random samples, we know that approximately 68% of all the samples I could take would produce an arithmetic average of some variable that lies within that boundary, that is, lies between 99.25 and 100.75. Similarly, what lies plus or minus 1.96 standard deviations? Well, we know that 95% of a normal distribution lies within 1.96 standard deviations of the mean, But what does it mean here? It means that 95% of all the samples we could take would produce an arithmetic average of some variable that lies in that area, and in this case, between values of 98.53 at the low end and 101.47 at the high end. Mostly statisticians feel that things in that particular region of the curve are pretty typical and are pretty good estimates of the population parameters. And typically statisticians tend to think of samples that fall outside that region, that is in the shaded gray areas in that graphic, as being atypical or bad estimates of the population, will produce statistics that are bad estimates of the population parameters. The paradox here is that in taking a particular sample, remember we only get one, we don't actually know if it falls in the middle region, which is the good region, or in the tails, which is the bad region. Here's another way of thinking about this. Here's a normal distribution that represents a sampling distribution of means. The vertical bar in the middle is labeled mu bar, which is, mu sub y would be the same thing here. It's the mean of the population. As we move from that mu out, we get to plus or minus 1.96, and that represents 95% of all the samples we could take. If we move the bars a little further out, going from minus 1.96 to minus 2.58, and going from 1.96 to plus 2.58, we're going to capture 99% of all the samples. And where did that number 2.58 come from? The Z table in the back of the book. Because we know that if we move plus or minus 2.58 standard deviations from the mean, we capture the middle 99% of a distribution. And similarly, if we move the bars even further out, so that we capture 99.9% of all the samples, we can say that 99% of all the samples fall plus or minus 3.29, sometimes I round this number to 3.29 standard deviations from the mean. And again, statisticians, whichever boundary we use, think of samples that fall in the tails as providing bad estimates of the population parameter, and samples that fall between the brackets, between the lines, as providing good estimates. Well, let's look at the standard error in a little more detail. The standard error is sigma sub y bar equal to 15 divided by the square root of 400. The 15 here is the standard deviation of the population, and the 400 is the size sample that we're taking. Again, we get a standard error of 0.750. And I've shown again how to construct a 95% confidence interval around the population mean of 0. On the other side of the screen, notice now that I'm dividing by the square root of 1600. That is, my sample size has increased from 400 to 1600. And notice that my new standard error, 0.375, is considerably smaller than the original standard error of 0.750. And again, below that, I've calculated the actual confidence interval. At the bottom of the screen, if I take the ratio of these two standard errors, I get 0.5, or 1/2. So what's going on here? Think back to the central limit theorem, or go back and look at that slide. It said as the sample size increases, we get a more normal distribution, and we should envision that our standard error will get smaller. Why? Because we divide by the square root of the sample size. So if sample size gets bigger, then the standard error, sigma sub y bar, has to get smaller. Now there's a particular pattern to this, and you can see it in these numbers. I didn't pick 400 and 1600 randomly. I picked 400, and I picked the 1600 to be exactly 4 times larger. And what this is telling us is that your standard error, the amount of error in your estimates, decreases by 1/2 every time you increase your sample size by 4 times. When you're doing survey research, probably the most expensive thing you do is collect data. So this is a little bit of cold comfort. On the one hand, we know that we'll get better estimates with larger samples. On the other hand, we probably nearly quadruple our cost of collecting the data by getting larger sample sizes to cut the error by 1/2. What's the effective confidence interval size? Well, we've been using a 95% confidence interval, and we know that the z-value associated with that is 1.96. So again, on the left side of the screen, I'm calculating a standard error from a population that has a standard deviation of 15 and a sample size of 1,600. On the right side of the screen, I'm calculating the exact same standard error. The difference between the left side and the right screen, though, in terms of the confidence intervals, is that on the left I'm using 1.96 for a 95% confidence interval. And what this means is that 95% of all the samples I could draw by chance and chance alone would produce an average value somewhere between 99.27 and 100.74. On the right-hand side, I've substituted 2.58 for the 1.96. Again, that 2.58 and the 1.96 are numbers I've taken from the Z table in the back of the book, and they represent, respectively, numbers that cut off the middle 95% of the distribution and the middle 99% of the distribution. The confidence interval for 99% confidence interval extends from 99.3 to 100.97. If I wanted an even wider confidence interval, I could use 3.29 instead of 2.58 or 1.96. As we use larger z values here, our confidence intervals get wider. And again, there's no free lunch with this. This is like saying when you go to the state fair and you play the game where, to win a stuffed animal where the carny will guess your weight. They could say, I'll guess your weight plus or minus 3 ounces or plus or minus 200 pounds. You'll probably play one game and not the other. But from the carny's perspective in years 2, you know that there's a great deal of confidence the wider the interval, plus or minus 200 pounds, he's going to guess your weight. Okay? So we're balancing here the precision of our estimate with certainty. One last thing we can think about. Here I've drawn this normal distribution again, our sampling distribution. And I'm showing in the middle that y bar sub y bar equals mu sub y. And what we've done in the past is put a confidence interval around the mean of 0, that is a z-score of 0. Now what I'm going to do is reach into that population, pull out a sample, calculate an average for the sample, and put a confidence interval around that sample, not the sample mean, not around the population mean. It's going to accomplish the same thing, but it kind of reverses a little bit of the logic and gives us another intuition about standard deviations and sampling distributions. Down below, I've drawn a vertical blue line that represents the mean of the population. The mean of the population is a fixed parameter. It doesn't change. It's always the mean of the population. Those horizontal bars, the 2 that are pink and the 4 or 5 that are blue, represent different samples, their means, and confidence intervals. Now you can see that the blue samples are very close to the population parameter, and in fact the population parameter is captured or falls within the confidence interval associated with each of those samples. If I used one of the means from the samples that are colored blue as an estimate of the population parameter, we'd think it's a pretty good estimate. Why? Because the actual population parameter falls within that interval. It's captured by the interval. So those 5 blue samples provide good estimates of our population parameter. On the other hand, if I provided a mean and a confidence interval associated with the 2 pink samples, you can see that those 2 samples have means that are very far away from the population parameter. They also provide estimates of the population parameter, but they're not very good. One is way too low and one is way too high. But I don't really know which is the right one. Of course, in this example, I can see that I'd prefer a blue one versus a blue sample versus a pink sample. But remember, in the real world, practically speaking, you're going to take one sample and that's it. But what I like about this is that I know that 95% of all the samples I could take would produce a mean with a confidence interval that in fact would capture the population parameter. And the larger my sample size, the smaller my confidence interval, and the more precise or more confidence I would have in my estimates. So to conclude, this slide shows us that in general, I can calculate a confidence interval for any desired level of confidence. What I need to do is define what z sub alpha divided by 2 is. Alpha is a number like 0.05, 0.01, 0.001, and it represents the area in both tails of the distribution. For example, if I want to use a 95% confidence interval, then I have 2.5% of the distribution in the lower part of the distribution and 2.5% in the upper part, that is 0.05. I'm isolating the middle 0.95. I divide by 2 because I'm interested in one tail or the other. I need to only look at one tail to make this estimate. So z sub 0.05 divided by 2 is z sub 0.025. When I go to a z table and look this value up, that is a place in the z distribution that cuts off the top 2.5% from the bottom, I'll find that I get a z-score of 1.96. And in this little table to the right, you can see that for our different alpha values that we typically use, 0.05, 0.01, and 0.001, that are associated with, respectively, confidence intervals or confidence limits of 0.95, 0.99, and 0.999, we get the z-scores from the z-score table of 1.96, 2.58, and 3.29. I hope this helps you understand this a little bit, and we're going to have another video shortly on how to actually calculate confidence intervals based on real data.